Hello everyone. Today I will be talking about nanowire lasers. The research into nanowire lasers is being driven by potential applications in areas like photonic integrated circuits, fiber optic communication, ultra-sensitive sensors that can detect explosives, for example, ultra-high density hard disks that could have 10 terabits of data per inch, and high-resolution photolithography. The broader impacts of nanowire lasers will be discussed at the end of the presentation. The history of laser development began in 1917, when Einstein first proposed stimulated emission. In 1954, three researchers at the University of Columbia developed the first microwave amplification by stimulated emission of radiation device. Soon after, in 1959, Gauss proposed the feasibility of a similar device for the visible spectrum, which he called the laser. The ruby and helium neon lasers were developed in 1960, with a number of inventions like the barcode scanner and transatlantic fiber cable following. The nanowire laser was only developed 15 years ago, and the spacer is the most recent major development. The first nanowires were made from zinc oxide and grown from silicon on a sapphire substrate using a vapor-liquid-solid growth mechanism and a gold metal catalyst. This bottom-up approach to fabricating nanolasers is less time-consuming and complex, with the synthesis of zinc oxide nanowires taking just 5 to 30 minutes after preparation. Next, we will go over a quick review of the operation of traditional semiconductor lasers, as the same principles apply to nanowires, although there are important differences. Spontaneous emission is when an incoming photon with energy greater than the band gap is absorbed with some probability and excites an electron to the conduction band. The electron then recombines with the hole in the valence band at some later time and emits a photon, with the probability of absorption equaling the probability of spontaneous emission. In stimulated emission, there are already many more electrons in the conduction band than valence band edge due to population inversion, and an incoming photon with energy greater than the band gap causes an electron to recombine with the hole and emit a photon in unison with the incoming photon. To construct a semiconductor laser, a degenerately doped P plus N plus junction is formed, and the top equilibrium diagram results. Under forward bias conditions, the Fermi level for electrons and the Fermi level for holes separate and population inversion occurs, as shown in the bottom diagram. This can also occur by optical pumping for 3-5 semiconductor gain mediums, whereby light from another laser, for example, is used to excite electrons to a higher energy state. The many inverted electrons that are within the depletion region, or within a diffusion length of the depletion region, can then recombine with the many holes in the depletion region and emit light in unison under stimulated emission. The increase in electron and hole concentration within the depletion region also increases the refractive index so that it acts as a waveguide for the emitted photons. The active laser medium is the source of gain, or amplification, in a laser in which energy from the medium is transferred to the emitted E&M wave, with the ruby acting as the active laser medium in the diagram below. The optical cavity of the laser is the arrangement of mirrors surrounding the gain medium that forms a standing wave cavity resonator that serves to increase the intensity of the light emitted, and is shown by the partially reflective coatings on the ends of the ruby shown below. The lasing threshold is where the dominant mode of recombination is stimulated emission rather than spontaneous emission, and is achieved when the optical gain of the laser exactly cancels the sum of the losses of the light during one round trip through the optical cavity. The lasing threshold, shown on the graph to the right, is around 20 milliamps, and it can be described by the equation below, where gamma is a confinement factor, G is the material gain, alpha subscript m is the mirror loss, alpha subscript p is the propagation loss, L is the cavity length, and R1 and R2 are the effective reflective coefficients for each end facet. Next, let's look at the difference in function of a nanowire laser. Nanowires are essentially one-dimensional semiconductors with diameters on the order of tens to a few hundred nanometers. An advantage of nanowires is that they act as both the optical gain medium and optical cavity. The optical cavity in a nanowire seems to act as a Fabry-Perot cavity, which is when there are parallel partially reflective surfaces at each end of the device. Nanowire arrays have been shown to emit a spectrum ranging up to a few hundred nanometers, as a result of the careful control of the temperature gradient and/or composition gradient during growth. Unlike large semiconductors, there are no problems of lattice mismatching that could occur when alloying is carried out to vary the band gap and thus the emission spectrum. Certain single nanowires have also been shown to emit a range of wavelengths when they are compositionally graded and are bent into a loop. The confinement factor in nanowires, which was gamma in the previous equation from the lasing threshold, could theoretically be larger than 1 due to the strong wave-guiding nature of the nanowires, as the wave propagation length may exceed the axial length. This would make it easier for the nanowire to reach the lasing threshold and would thus correspond to lasing at a lower level of excitation. One nanowire device that is under current research is a surface plasmon polariton laser, or SPP, that is made with a cadmium sulfide nanowire and is shown in the diagram below. The reduction in nanowire diameter is limited by the diffraction limit, which is around half of the optical wavelength in the medium. However, SPP waves, which are the collective oscillations of electrons on the surface of a metal, have much shorter wavelengths than photonic wavelengths of the same energy. Thus, these waves that are transmitted to the nanowire allow it to emit optical energy far below the diffraction limit. This means that lasing can occur at much smaller diameters for SPP devices than for traditional nanowires, as shown on the graph at the right. Nanowire lasers made from lead halide perovskite are the most efficient in existence. Under room temperature lasing conditions, they showed the lowest lasing thresholds and highest quality factors reported to date. They have nearly 100% quantum yield, which in this case is the number of electrons that recombine and emit a photon per incoming photon, and their emission spectrum range from infrared to blue with decreasing halide number. The smallest lasers that are currently experiencing widespread commercial application are vertical cavity surface emitting lasers, or VCSELs, with an example shown in the figure at the bottom right. The main differences between VCSELs and nanowire lasers are that VCSELs are fabricated with more layers and emit light perpendicular to the top surface, unlike edge-emitting lasers like the nanowire. While VCSELs are used mainly in applications like optical fiber data transmission and analog broadband signal transmission, nanowires may have more potential in photonic integrated circuits. Because the VCSEL emits light perpendicular to its top surface, in contrast to edge-emitting nanowires, it can be tested throughout the manufacturing process, while nanowires cannot. A major issue for many nanowire laser devices, like the SPP, is that it is optically pumped, which is undesirable for commercial applications like optoelectronics, as it requires an external source. Another issue for many nanowire devices is metal loss of optical energy due to electron scattering in a metal, although this has been minimized for SPPs through the use of a magnesium fluoride dielectric spacer between the nanowire and metal. While control of the doping profile has been shown for nanowires in a laboratory setting, the reproducibility must improve in order for a wide emission spectrum to be commercially feasible. The structure of nanowires also makes them susceptible to damage from moisture. Further research is needed on nanowires' power efficiency, lifetime, reliability, and reproducibility before they can experience widespread commercial utilization. One area where nanowires could have a very large impact is in optoelectronics and specifically photonic integrated circuits due to their small size and potential for ultra-fast operation. Researchers were able to get up to 100 times faster internet speeds by using a PIC switching mechanism. More research into different manufacturing processes can also lead to lower-cost electronic devices like phones and computers with much faster operation. However, using nanowires that contain heavy metals like cadmium sulfide in optoelectronic devices could have far-reaching negative effects on human health and the environment, as e-waste can end up in other countries where people without the proper protection could handle it. Because of the reduced size of nanowires, they can be integrated with other components on a single platform to provide new functionality in areas like nanofluidics-based biological and chemical detection. As perovskites are also actively being researched for solar cells, breakthroughs in researching their application for nanowire lasers could also greatly benefit solar cell research. Here is a list of my references. Thank you for watching.